All right, we've got a little bit out of order. So this isn't actually week 4. Let's correct this. It's actually week 5. But I think the new order, Alston's suggestion, is a good one. So here we are in week 5 doing spur gear bending. It's a quick review, a bunch of different types of gears. Spur is the most basic, the one that you picture when you picture a gear. It's only one of many. We've talked about these. Again, the spur gear is the one that we're going to be looking at. It's the simplest, but to give you a sense of all the trade-offs involved with gears. Terminology, remember for inch gears, English units, it's N per D, right? So it's number of teeth per inch of pitch diameter, so it's teeth per inch. Whereas for metric gears, millimeter gears, it's the opposite. We say millimeters of pitch per tooth. Okay, so P and M are just upside down of each other, big P and M. Okay, so anyway, and we discovered that we've got a speed problem when the tip engages. So fast tip, and then down here is a slow root, right? Because things are moving at different speeds. As we move along the radius, we have to do something special, right? And the special thing we do is make this involute gear geometry, the involute curve, and then we wind up the ratio of angular velocities always remains constant. All right, so that way they mesh smoothly and continuously, and it's not a jerky, violent motion of gear tooth engagement. All right, there's a lot of geometry involved. We're not going to get into that too much anymore. But gear design, it's an art into itself. We could have a whole class, more terminology. Oh, yeah, no, this is new. Pop quiz. Let's see, we know 3 important facts about the bending moments, right? Moment increases linearly with distance from load. In other words, let's do this in blue maybe. So the moment equals a function of x, all right? And let's just draw, no, we'll just leave that. Okay, stress decreases inversely with the second moment of area, and I increases, so sigma equals mc over I, but I equals a function of h cubed, right? So what does that mean if we put these two things together? That means that sigma equals, well, c is actually h, so it's m times h over h cubed, right? Which means that sigma equals, well, it's proportional to, I should write, m over h squared. Right. Now let's take a look at this. So here's the pop quiz. What cantilevered beam profile will result in a uniform stress along the length of the beam? I'm going to draw a coordinate system here. I'm going to say that this is x that way. And so that, and I know that the moment is, so there's 0 moment here. So m equals 0 there, m equals max there. So I'm going to say that moment equals some function of x linearly, which means that sigma is proportional to x over h squared. So if I want my stress to be constant, and I say what profile, I'm going to solve for h, so h equals h squared equals x over sigma. Sigma's constant, h has to equal, whoop, those are supposed to be proportional. Let's fix that. Those are proportional. So the height has to be proportional with the square root of x. In other words, the profile that we want is a parabola. And you might have done this in 306, I'm not sure if you do. So this is a parabolic profile, right? So if I wanted a cantilevered beam and I wanted the stress to be the same everywhere, I would make it a parabola. That way the stress is constant. I'm not wasting any material to have excess strength where I don't need it. All right, so that's kind of interesting, but what does it have to do with gears? Oh, look at that. I could take this parabola here. That's a parabola. And fit it pretty neatly inside of an involute gear tooth. All right. And so that means really that the stress is pretty constant. Where is the, that's labeled right here, I forgot that. Where is the, where does the parabola most closely match the gear tooth? Right here. So matches the tooth there, all right? And so if we look at this, sure enough, right, this is, I'll put that, circle that in red maybe. That spot right there looks like it's the highest stress. Right, because that's where the parabola matches the gear tooth. Notice there's also some action here. Right, I wonder what kind of stress that is. Anyway, that must be a contact stress and then the base fillet, right? So that's where the stresses are. And as we mentioned at the start of this, we're going to talk about gear tooth bending today. All right. Well, what is the load on the tip of the tooth, right? We need to know this load. What is this? Right, or how much is that, or what's the magnitude of that force? This, this causes bending, but this doesn't. Right, but we need to know what that tangential force is. All right, now your book gives some absolutely bizarre equations. Right, and I can't stress this enough. You will not survive plug and chug equation manipulation, right? That's not what this course is about. That's what engineering is about, for that matter. So please don't use these equations in the book that have all these unit conversions built in, from horsepower to foot-pounds to torque, whatever, and all these bizarre relationships. Use these, right? That power is torque times speed here, and then the torque is the force, the tangential force times the radius, and the pitch line speed is the radius times omega, right? And this is not W, this is lower case omega, right? Angular velocity. So that's that, right? Uppercase omega looks like that. Anyway, please use fundamental equations of power is torque times speed, torque is force times radius, and velocity is radius times omega, angular velocity, right? So that's just a side note, because people get lost. Well, but there's this equation in the book. Yeah, don't use the equation in the book. Use stuff that you know. That being said, here's a bunch of equations, right? There's really two approaches to figure out the bending stress. One is what's called the Lewis equation, right, which is pretty simplistic, but it's a good place to start. There's a long list of assumptions here, right? Neglect the radial force. Yeah, that's fine because it really doesn't cause any bending. The entire load acts at the tip. That's worst case. A uniform force distribution. What does that mean? That means that along this whole length of the force here, right? This is all uniform. Now, in a perfect world, if my gears are mounted on perfectly parallel axis shafts, sure. Are they mounted on perfectly parallel axis shafts that never deflect? No, right? So this is, that's quite an assumption, right? They may be misaligned slightly, and then a whole bunch of them, no stress concentrations, no sliding force, no contact velocity, right? We'll talk about those in a little bit. So if we make all these assumptions, we know that the bending stress is just MC over I. We just talked about that. We know that the moment is the tangential force times the height, right? Here's the height, so that's nothing new. There's a little funny geometry that goes on, that this distance C, where is C on here? I don't have it on this picture, I think. But the moment of inertia is 112bh cubed, or bt cubed, when we use that as the t. A bunch of plugging and chugging happens, and we wind up with a nice, neat equation for sigma, right? Sigma, stress, right? So the 6, it comes out of the algebra, the tangential force, we know that. H, we don't really know the H. We also don't really know the T, right, which is the thickness of the tooth at the base. We do know the face width, so we know that, but we don't know these other two things because they depend very largely on these subtle gear geometry things, right? So undercut here, so this little thing down here is what we refer to as undercut, this little shape here, right? I think we talked about that. That's undercut, and that's to reduce, to eliminate actually interference. And that the geometry for that is super, super complicated. So to actually get an H and a T is pretty tricky. So as with all things 342, there's a figure for that. And what we have to do is, we combine. We're going to combine combine the difficult geometry, right, into the 6h over t cubed, and we're going to call that the Lewis form factor, right? And so we know the tangential force, we know the face width, we know the pitch. What is pitch again? Number of teeth per inch of pitch radius, pitch diameter. And then we have this Lewis form factor, which comes from this plot, right? So you know the number of teeth, you know what the contact angle is, and then you figure out your Lewis form factor. All right, so easy example here. I've got 100 pounds of tangential force. I know that I've got a pitch of 4, and I don't give it. The number of teeth is 28, right? So I got to go to contact angle of 20 up here, and I go to 28 down here, and so I go to here, and sure enough, yeah, about 0.35. So I plug this in, into this kind of condensed bending equation here, and then I wind up with 11.5 KSI of bending stress, right? Which is ballpark what steels can withstand. Next page. All right, now that's a very simplified version. The slightly more elegant way is AGMA, right? That's the American Gear Manufacturers Association. So again, this is a group of industrial, players, right? Manufacturers or designers, and they got together and said, hey, let's decide on a way to do this. And there's no laws about this. There's no rules. It's not fundamentally, based in physics. It kind of fundamentally based in physics. But they got together and said, let's agree on a way to calculate this stuff, which I think is kind of neat. We're still going to neglect the radial force. We're still going to assume that the entire force, the force acts at the tip, because that's still the worst case. No sliding force, right? There might be some friction, but no sliding force. We'll assume that, or we'll allow for misaligned gears, right? So what does that mean? If you imagine the gears as kind of like two hot dogs rolling together, those hot dogs might not be perfectly parallel, and so there might be more load at one place than another. We're going to allow for stress concentrations at the base fillets, and we're going to say that they're going to hit each other with some velocity, right? There's going to be some impact involved, right? So what we do, it looks very, very similar, except now we have a J, which is the AGMA geometry factor, and then of course there's a factor for that. We've got a mounting factor, how well are they aligned? An overload factor, is it always nice and smooth, or is it kind of a jerky load? And then the velocity factor, how fast are these things spinning, and when they hit, is there some dynamic load involved in that? All right. So it's important to note that these factors, right, increase the stress. These factors increase the stress. Other times we've used factors that decrease the fatigue strength or the endurance strength. In this case, we're going to say these factors increase the stress. It's very, very important to look at this and say, what do these factors do? J, in this case, reduces stress. A bigger face width, a really long gear, of course that reduces stress. More tangential force, of course that increases stress. But this is new here. These guys also increase the stress. All right. So the geometry factor, it's very similar to the Lewis form factor, but it just includes a stress concentration, right, due to the radius of the tooth root. And so down here we can say no load sharing. So contact ratio, how many teeth are engaged at the same time, equals 1.0, right? And then up here we say, in reality, there is some contact sharing, right? Okay, so what does this do? The geometry factor J, right? Does this make sense? If there's load sharing, it reduces my geometry factor, it increases my geometry factor. So what happens if I increase my geometry factor? Oh, it reduces the stress. This makes sense, right? Allowing the teeth to share the load increases the geometry factor and then decreases the effective stress. All right, good. So you have to look at these equations and say, does it make sense, right? Based on your quizzes, I get the feeling that some of you are doing this and some of you aren't. So please just don't look at these and say, well, this is the equation I used to plug in numbers. Don't do that. Look at it. Say why. Well, we're not going to go through and derive these curves, right? We're not going to go through and derive these curves. But you have to say why is why there, and do that. All right. Okay, velocity factor, right? There's two things that affect this. How well are they manufactured? So this is, let's see, do this in a red, because that's in blue already. So this is increasing quality. And then how fast are they actually hitting each other, right? What is the actual tip velocity of the tooth, right? And then we get that based on the diameter or the radius and the and the angular velocity, right? So really, really high. As we increase the velocity, that increases the velocity factor. As we increase the quality, that decreases the velocity factor. Does that make sense? Ask yourself, does it make sense? Go back to these equations. Say, does that make sense? Yeah, it does. All right. Overload and mounting factors, right? So this is basically the alignment of gears. And that means, along the face width, are they sharing very nicely, right? So if I do a really nice job here, precision gears, small bearing clearances, blah, 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 small face width, pretty low, right? But even the lowest I go is 1.3. What does that do? 1.3. Oh, 1.3 means that's a 30% increase in my effective stress, even if it's the best I can do. That's interesting. And likewise, if I've got like an electric motor, let's make a note of that. So this is like electric motor, driving maybe like a water pump, right? Really nice and smooth. And this would be, say, Harley Davidson on, let's say, bumpy road. Right. I always use Harley Davidson as my example because the way they get that, the classic sound is the way they arrange the pistons on the crankshaft. But anyway, it's a really, uneven driving power, and the bumpy road would mean there's, you know, whatever. You get what I'm saying. I'll stop rambling here. But again, both of these, you know, best case it's 1.0, worst case it doubles the stress. All right. And then finally, fatigue analysis here, right? We have to consider the fact that this gets loaded, unloaded, loaded, unloaded, loaded, unloaded. Oh, wait a minute. Loaded, unloaded, loaded, unloaded. So we call that a repeated loading. So it's not fully reversed. Okay, that's, well, anyway, let's look at this here. So, of course, we have the gradient factor. So if we have really big teeth, we'll call, or if we have small teeth, it's called a 1.0. If we have big teeth, it's 0.85. Obviously, there's a continuum in there, but we're simplifying this. It's bending, right? 1.0. Surface finish, right? We got to look that up in that old table with you know, salt water and whatnot. Reliability factor, of course, we've been through that. Temperature factor. Now, it's very possible that gears are operating in pretty hot environments, so we might actually have to consider this. And then this KMS, I don't know what that is. 1 for two-way bending, 1.4 for one-way bending. Okay, whatever. And then of course we do the usual thing, compare, you know, the stress and the endurance limit, right? And that gives us some safety factor. But for fatigue analyses, we're supposed to do a Goodman diagram, right? What happened to our Goodman diagram? Here we're just comparing, but is there a mean stress or not? Okay, we better take a closer look at that. I wanted to use it. We spent so much time learning Goodman diagrams, and now we don't. All right, so one-way bending, right? That is where, so for instance, this driving gear here, right there, it gets bent. So this tooth will get bent back and then released, and then bent back and released, and get bent back and released, and get bent back and released, right? So that's only a one-way bending, so that's a repeated load. What happens with a repeated load? The mean and alternating stresses are each half of the force, right? Or half of the stress. And so that means we do have some mean stress in here. Ooh, mean stresses are bad. But if we look at this idler gear, right, this gear is in the middle, this tooth gets bent forward. So the tooth bent forward here, right? Why? Because it's getting pushed on in the direction it's turning. But then here it becomes a driving tooth, and then it gets bent back. So this is a fully reverse loading, right? So we need to, oh shoot, I didn't leave myself any room to write. Yeah, okay, well, so it is. Well, maybe I'll have to zoom in and draw down here. So if we're to zoom in and make actually a Goodman diagram, which is what we're supposed to do for these fatigue problems, and I said this is SUT here, and this is SN here, this is sigma alternating, this is sigma mean, and I draw this, all right? But for a repeated load, it goes at a 45-degree angle, repeated 45 degrees, or m equals 1, not m, slope equals 1, right? What does that do? It effectively, adding this mean stress in, but it's a known mean stress because it is, it's at 45 degrees. And if we say this is about 0.5 SUT, right, then really we know the slope here, we know SUT, we know half of SUT, so this all works out to be the same every time. So we have effectively a lower endurance strength, right? But, right, so effectively a lower endurance strength. There, right? But, let's see if I can make room here. But, sigma M equals sigma A, which equals sigma over 2, right? So it's only half the stress. If you go through and do all the algebra, we discover that it works out to be about 0.43. The stresses work out to be about 0.43 of the ultimate tensile stress. Divide that by 1 over 0.43 is about 1.4, right? So that's why, because while we did reduce the endurance strength by a little bit, we also cut the alternating stress in half. So it works out to be about a 1.4, right? So KMS is 1.4 for one-way bending and 1.0 for two-way bending. And so what does KMS do? KMS, oh, so that's interesting. That increases strength, right? Now, did it increase the strength or did it reduce the effect of the the two-way bending? It's the same thing. Algebraically, it's the same thing. So in these cases, well, for gears in general, our factors increase stress, but our factors also increase strength, right? And so that's the end of that. Go back. I don't know how to go back. Yeah, that's the end of that. So the basics on gear tooth bending, it's just looking up a bunch of factors. You got to kind of make some judgment calls based on this stuff. And then we really do things just the way we always do. Okay, that's it. Next one coming up.